Welcome student. This is Dr. Shubhram Das, Assistant Professor, Department of Computer Science and Engineering, Narula Institute of Technology. Subject Data Structures. And today I'm going to discuss the topic tree, and the main topic of today's lecture is construct a binary tree from a given traversal sequences. And later on we will discuss about threaded binary tree. So first, how do we construct a binary tree from a given pre-order and in-order sequence? So in this example, pre-order and in-order, these two traversal sequence are given. So using this sequence, we have to construct a binary tree. So how do we construct that binary tree? So now look at this pre-order. We know that in pre-order sequence, root always stay at the first. That means this is my root of the tree. That is A is my root of the tree. So then we can write down, so root is A. So now in order, root always in between left subtree and right subtree. So where it is A, so A is situated over here. That means left side all are the value of the left subtree, and right side all the data are values of the right subtree or part of the right subtree. So we can write down in this way all left subtree part of that is D, G and B. So we can write D, G and B. And in the right subtree, so they are the part that is H, E, I, C and F. Now question is, who is the root among this D, G and B? So from this D, G and B, in pre-order, always root come first. That is B will be the root of this DGB. So we can write down. So A is the root. Then next is root is B. And D and G are the part of the left subtree. That is D and G. So now among this H, E, I, C, F, who is the root? So that means we have to first find out from left side to right side in pre-order. So who will situated in the first is the root of this right subtree. So that means from H, E, who is come first? That is E. E come first. That is among this H, E, I, C, sorry, C came first. That is C. So that is C came first. That means C will be the root among this right subtree. So that means we can write down C will be the root, and right side of the C only F is there. So we can write F, and all are, that is H, E and I is the part of the left subtree. So that is H, E and I. They are the part of the left subtree. Because if C is the root, then only right side is the F, and all are part of the left subtree. Now among this D and G, who is the root? So that means who come first? That is D come first. So that means D is the next root among this D and G. So A is the first root, then B, then over here C, then root will be the D. So next, G situated at the right side of the D. That means G should be right subtree of G, or right child of G. So now F is also here, and now find out the root among H, E and I. So H, E and I, among these three nodes, so E is situated first, or he came first in pre-order sequences. So E should be the root of this subtree H, E and I. So if E is the root, then right side I is situated. So I is situated at the right side. So I should be the right child of E, and H should be the left child of the E. So this is my final binary tree. So it is level 0. This is my level 1. So this is my level 2. And this is level 3. So this is the final binary tree. Final binary tree using this given pre-order and in-order sequence. So next, we have to discuss how do we construct a tree if in-order and post-order sequence are already given. So in post-order case, we know that root always situated at the last, or in the sequence. So at the last, the root will come. So that means A is the root of this tree. So now we can write down A. A is the root. Now find out in order sequence where is A. So A is over here. That means this is my root. So all these three are the part of the left subtree, and right side all are part of the right subtree. So now we can say that is D, G and B are the part of the left subtree, and H, E, I, C and F part of the right subtree. So now who will be the root among D, G and B? So in post order, we always check our root from the right side to left side if I go through. So then C, F, E, I, H, B. So B come first among D, G and B. So B will be the root. So then we can write down A, then B. So now D and G is situated at the left side of the B. So they will be the part of the left subtree. So now among this H, E, I, C, F, who is the root? So we come from left side, so C. So C come first, that means C is the root. So we can write down C is my root among the subtree, and right side of the C only F is present. We can write down F, and all H, E and I are part of the left subtree. It is H, E and I are the part of the left subtree. So now among this D and G, who is root? So D come first. That means from the right side to left side, D come first. That means D is the root. So we can write down A is the root, main root of the tree. Then left child is B, right child is C. Then it is D, and G is situated at the right side. That means it should be a right child of D. Now F is here. Now among this H, E and I, who is the root? So E come first. That means E will be the root. So we can write down E. Now if E is the root, then H is part of the left subtree and I should be the part of the right subtree. So that is H is part of the left subtree and I will be the part of the right subtree. So this is my final tree. So this is my final binary tree using the given in order and post order sequence. We can also check with this previous one, that is it's also A, B, C, D, E, F, then G, H, I. So that is the same tree you have taken for this in order, pre-order and post-order sequences. So it is the final binary tree. So we already learned how can we construct the tree if in order with pre-order is given or in order and post-order is given. So now next we'll learn what do you mean by threaded binary tree. So in threaded binary tree, before going to start the threaded binary tree, we already know that how can we represent a binary tree with the help of linked list. So this is the node. So inside this node, this is the data part, and the left side, it is stored the address of the left child, and this is the address of the right child. So this is my data part, and this is my previous left child, or this is my next or right child, or you can say that is left and this is right. It will hold the address of the left child, it will hold the address of the right child. So from the left child of A is B. So the address of the B will store over here, and address of the C will store into the right side or in the next part. So in this way, we can represent the binary tree with the help of linked list. Now look at the tree very carefully. Here some null pointer is there. That means this null pointer means this is also denoted by in these symbols, that is null, that is also ground. So this one is indicate that is no node further present. So that is the leaf node. We can denote it in the both left and right side is null. So first count the how many nodes are there in this binary tree. So 1, 2, 3, 4, 5, 6, and 7. 7 nodes are there. So if I count n is equal to, n is the number of node, it is 7. Now calculate how many null pointers are there. 1, 2, 3, 4, 5, 6, 7, 8. So 8 null pointer is present, it is 8. And how many non-null pointer? That is 1, 2, 3, 4 and 5. So 5 pointer is present, that is not null. So now we will discuss about the threaded binary tree next. We just observe this tree. So number of node is 7, number of null pointer is present 8, and number of normal pointer is present 5. So now threaded binary tree. So in the above binary tree, there are 8 null pointers and actually 6 pointers. So we have to count wrongly. 1, 2, 3, 4, 5, 6. Sorry, 6 normal pointer is present. So 6 actual pointers are there. So in all, there are 14 pointers and number of nodes are 7. So now we can generalize this form. That is, if my node number is n, there are n plus 1 null pointer should be there, and 2n total pointer should be there. That is, total point is null pointer 8 and actual pointer 6. So 8, 6, that is 14 total pointer, and number of nodes is 7. So that is, if n is number of nodes, then 2n is total number of pointers, and where n plus 1 number of null pointer present. Now the objective here to make effective use of this null pointer in the threaded binary tree. So for this reason, A.J. Perlis and C. Thornton jointly proposed an idea to make effective use of these null pointers. According to this idea, we are going to replace all null pointers by the appropriate pointer values called threads. And binary tree with such pointers are called threaded tree or threaded binary tree. So in the memory representation of a threaded binary tree, it is necessary to distinguish between a normal pointer and a thread. Thread actually replaced by this null pointer. So now what is the necessity? Actually, we have to traverse all the nodes of the binary tree. We can efficiently traverse without help the stack. This is another important point. So now, what is threaded binary tree? So threaded binary tree, we can distinguish in two different types. Number one-way threaded binary tree, and another is two-way threaded binary tree. First, we discussed one-way threaded binary tree. So now let's one example and we discuss. So first, we will have use the right threads only in this case in one-way threaded binary tree. And to implement threads, we need to use in-order successor of the tree. Let's take an example. So now this is a normal tree. We already write down in the previous example, that is A, B, C, D, E, F, G. There are so many null points are there. So now we have to first take the in-order traverse. So what is the in-order traverse of this tree? So in-order means root always in the middle. So that means in-order traverse should be first D. So D is there. Then we have to, in order means root, then right. That is B, then E. So B, then E. So left subtree is complete, then root, that is A. And all are part of the right subtree, that is F, C, then G. So F, C, and G. So this is my in-order traverse of this binary tree. Now we have to replace this null pointer. Here actually null pointers are there, but we have to replace by these threads. threads also denoted by this dashed line, that is called threads. So why this null pointer indicates, so this or this null pointer hold the address of the B, because after D, so B is the in-order successor of D. So B is the in-order successor of D. So that's why this null pointer replaced by this address of B. So similarly, here also found null pointer, but we have to look at this. After, where are the null pointers are there? This one. So left side of D. So left side no nodes are there. So that means we cannot replace this one. So in B, no null pointers are there. So it is not, and no question arises to replace the null pointer. So here both null pointers are present. So now E. What is the in-order successor of E? That is A. So that's why, so it is only right pointer we have to replace by these threads. That is, we have to replace by these threads, and we have to indicate throughout towards the A. So now next, C. So C is the in-order successor of F. So that's why, so the right null pointer is threaded by this C. So that will hold the address of the C. And now look at the G. So no such values are there in the right side. So that is the ending. So that's why no value no null pointer we can replace by this, by no values are, or no threads are replaced by this null pointer. So null pointer remain unchanged. So now few of the null pointer we replaced by threads in one-way threads, but it has some advantage. So if I want to traverse, so we have to traverse first, we come to the root, then we can come to the B, then we go to the D. If there are two null pointers are there, so we cannot move anywhere. But if there is a threads, or this null pointer replaced by this B, so we can again traverse to the B. So next we come to the E, then we have to go back to the A, then in this using this address we come to the C, then F, then again back to C, again back go to the G. That means we can traverse all the nodes in this way. So take another example of threaded binary tree, or one-way threaded binary tree. So before going to what is the summarized, that is, we start at the leftmost node in the tree, print it, and follow its right thread. If we follow a thread to the right, we output the node and continue to its right. If we follow a link to the right, we go to the leftmost node, print it, and continue. So in this way, we have to traverse all the nodes. So now take one example. So it is my threaded tree, and first we go to the leftmost, that is over 1. We have to print, that is start at leftmost node, print it. That is 1 is my leftmost, we have to print it. Then we follow the threads to the right and print the node, that is 3. We have to print the 3. Then follow the link to the right. So in this way, we have to follow, and we have to go to the go to the leftmost node of and print. So this is my 5. So you have to print. Then you have to follow these threads to the right and print the nodes. That means 6 we have to print. So then follow the right link and go to the leftmost node and print. That is my 7. Then we have to follow the threads. So in this way we have to follow the threads and move to the 8 and print it. Then go to the leftmost, go to the link to right and go to the leftmost node and print this 9. So in this way we have to traverse all the nodes and we can visit or traverse and print the value. So now next, how do we represent two-way threaded tree, or what do we mean by two-way threaded tree? So two-way threading as left pointer of the first node and right pointer to the last node will contain the null value. So all other values or null pointer replaced by these threads. So in the one-way thread, only right pointer is replaced by the thread, but in two-way threaded binary tree, so both the pointer will replaced by the thread, only leftmost or first node, left pointer of the first node and right pointer of the last node remain this null value. So now come to the example. So here, so look at this, no null pointer are there except this one and this one. These two is called, that's why dangling. So these two null pointer remain there, otherwise all 9 null pointer replaced by some threads. So these green symbols are the threads, this one, this one, this is right threads, and this one is the left threads. This 3 line is the left threads and 2 line is the right threads. So here also in order traverse of this tree, we have to first check the in order traverse, then in order successor and in order predecessor, both we have to accept or take care. So what is the in the E, what is the in order predecessor? So that is B. So that means this null pointer replaced by this B threads. And what is the in order successor? That is A. So this null pointer is replaced by these threads of A. And similarly, F. So come to the F. Who is the in order predecessor? That is A. So that means we have to link with A. So who is the successor, in order successor of F? That is C. So then we have to replace the null pointer, or we have to thread towards the C. So similarly G, so only in order predecessor is present, no in order successor present. That's why this null pointer we cannot replace by threads. So similarly in D, no in order predecessor are there. That's why this null pointer remain there. We cannot replace by this thread. So now this dangling we can also overcome. We can solve this using introducing a header node, and the left and right pointer of the header node are threads at normal link and are initialized to point to the header node itself. Now look at the picture. Here these two null pointer are linked with this header node. So in this way we can replace all the null pointer using some threads. So now what is the advantage and disadvantage using threaded binary tree? First come to the advantage. So number one, by doing threading, we avoid the recursive method of traversing a tree, which does not use the stack and consume a lot of memory and time. Number two, the node can keep record of its route. Number three, backward traverse is possible. And number four, applicable in most type of the binary tree. Now, what are the disadvantage? Number one, this makes the tree more complex. Number two, more prone to error when both the child are not present and both the values of the node pointer to their ancestors. Number three, lots of time consumes when deletion or insertion is performed. So this is the summarized, that is what are the advantage and what are the disadvantage using threaded binary tree. Now we have to compare our threaded binary tree with the normal binary trees. In threaded binary tree, the null pointer are used as thread, but in normal binary tree, the null pointer remain null. We can use the null pointers, which is efficient way to use computer's memory. In normal binary tree, we cannot use null pointer, so it is a wastage of memory. So in threaded binary tree, traversal is easy, completed without using stack or recursive function. In normal binary tree, traverse is not easy and not memory efficient. In threaded binary tree, structure is complex. In normal binary tree, less complex than threaded binary tree. And threaded binary tree, insertion and deletion takes more time, but in normal binary tree, less time consuming than threaded binary tree. So this is all for today's lecture. So thank you for listening my video.